Okay, so we all know the seasons change, right? Summer, winter, it's a basic part of life. But do we really know why? You probably think you do, but what if I told you there's a whole other way to look at it? A totally different explanation. That's what we're diving into today. Two competing theories for something we experience every single year. Let's get right into it.
All right, let's kick things off with a real head-scratcher. It's summer, it's hot. Obviously, that means we're closer to the sun, right? Well, actually, nope. That's totally wrong. For those of us in the northern hemisphere, summer is when we're actually farther away from the sun. And that one little kind of weird fact, it's the key to this whole conversation.
So here's the game plan for today. First, we're going to break down the answer you almost definitely learned in science class. You know, the one all about the Earth's tilt. Then we're going to get into something a little more out there. A really fascinating and, yeah, pretty controversial idea about something called a charge field. We'll see how it's supposed to work, check out some pretty surprising math, and then at the end, we'll put both theories right next to each other to compare.
Okay, first up, let's talk about the textbook answer. This is the one you probably remember from school, the established, mainstream scientific view on why we have seasons.
And this right here really just blows that whole closer to the sun idea out of the water. Just look at the numbers. In July, peak summer in the north, we're clocking in at about 94.5 million miles away from the sun. But in January, the coldest part of winter, we're a full 2 million miles closer. So, yeah, if distance isn't the answer, what the heck is going on?
So here's the big takeaway. We've got to stop thinking about how close we are and start thinking about, well, about angles. It's all about geometry, really. The angle of the sunlight hitting the Earth, that's what matters.
And that brings us to the star of the show in the mainstream explanation, axial tilt. See, our planet doesn't spin perfectly straight up and down while it goes around the sun. It's got this lean, this tilt of about 23.5 degrees. And according to standard science, that little tilt is the whole reason for everything. The best way to get your head around this is the classic flashlight analogy. Imagine the sun is a big flashlight and Earth is a beach ball. If you shine that flashlight straight on, you get a really bright, concentrated circle of light, right? Super intense. That's basically summer. But now if you tilt the beach ball, that same beam of light gets spread out over a much bigger area. It's weaker, less intense. That's winter. So that 23.5-degree tilt is what makes one half of the Earth get that direct, powerful sunlight, while the other half gets the weaker, spread-out version.
All right, so that's the standard model. It's clean, it makes a lot of sense, and it's what's taught everywhere. But what if it's not the only way to look at the problem? What if there's a totally different model out there that can also explain why we have seasons? Let's dive into that.
And this is really the core of all scientific progress, isn't it? Just asking that simple question. Can we do better? Is the standard explanation really the final answer? Or could there be something else, maybe something deeper that we just haven't figured out yet?
And that brings us to the alternative, the charge field theory. Now, this idea pretty much flips the script entirely. It says the seasons have nothing to do with the angle of the sunlight. Instead, it's about the Earth moving through this invisible energy field coming off the sun. And get this, in this model, the Earth's tilt isn't the cause of the seasons at all. It's actually an effect of these bigger cosmic forces.
Okay, so you're probably thinking, how would that even work? Well, the key idea here is that Earth isn't just a rock sitting there getting baked by the sun. No, it's more like an active engine, one that's constantly pulling in energy from space and, believe it or not, recycling it. So in this model, that 23.5-degree tilt isn't some random accident. It's the result of a massive cosmic tug-of-war. You've got charge fields from the sun, from the giant outer planets, Jupiter, Saturn, and the others, and even from the center of our own galaxy, all pulling and pushing on Earth. Our tilt is just the sweet spot, the equilibrium point where all of those forces find a balance. This whole concept of charge recycling is basically the engine that makes the charge field theory run. So again, the idea is Earth isn't just a passive victim of the sun's heat. It's an active participant. It literally sucks in charge at the poles, uses its own rotation to heat it up, and then shoots that heat back out. Let's break that down into 3 steps. Step 1 is intake. The theory says the Earth is pulling in photons at the South Pole and antiphotons at the North Pole. Step 2 is heating. The planet's spin, its own angular momentum, acts like a generator and spins up this charge, creating heat from the inside out. And finally, step 3, emission. That warmed-up charge is then released from the surface, mostly around the equator, which causes the warming.
Okay, look, a cool theory is one thing, but the real test is, can it make predictions? Can it give us numbers that match reality?
This is where things get really interesting, because the charge field model tries to connect some numbers that, on the surface, seem to have nothing to do with each other.
So the first key number here isn't just our familiar 23.5-degree axial tilt. The theory says you also have to add our orbital inclination, which is basically the slight tilt of our orbit itself. You put those two together, and you get 33.66 degrees. Remember that number.
The second key number, 23 AU, or astronomical units. What's that? It's the average distance from the Sun of the 4 big outer planets: Jupiter, Saturn, Uranus, and Neptune. In this model, their combined charge field is super important.
And here is where it all comes together. The theory takes that combined angle, does some math to turn it into a ratio, and then divides that by the 23 AU distance of the outer planets. And the number it spits out is 0.0163. Now, I know what you're thinking. Okay, so what? It's just a number. But trust me, it's not just any number.
Because this is the big reveal. That number the theory calculated, 0.0163, that is its prediction for Earth's orbital eccentricity, which is just a fancy way of saying how elliptical or stretched out our orbit around the Sun is. And what's the actual scientifically measured value? It's 0.0167. I mean, wow, that is astonishingly close. The fact that you can supposedly use the Earth's tilt and where the outer planets are to calculate the shape of our orbit, that's probably the single most compelling argument for this whole charge field idea.
So, there you have it. 2 totally different ways of explaining something we all live through every year, the seasons. Let's wrap things up by putting them side by side. This chart really spells it out. The mainstream view says the primary causes are 23.5-degree tilt, which changes the angle of the Sun's rays. The heat source? Direct solar radiation. Simple. But the charge field theory says the causes are positioned in the Sun's energy field, and the heat source is actually internal, from that charge recycling process. So in one model, the tilt causes the seasons, in the other, the tilt is just an effect of bigger forces. It's the simple flashlight analogy versus a theory that pulls off a really surprising mathematical prediction.
And all of this really leads to a much bigger question, doesn't it? One that's about more than just why it's cold in January. How does science actually move forward? What does it take for a new, maybe kind of weird idea to actually challenge a model that we've accepted for hundreds of years? Is it just one shocking calculation? Or a whole new way of looking at the same old facts? Well, that's definitely something to chew on. Thanks for coming along for this one.